अच्छा एक सेकंड, यूट्यूब के ऊपर भी अपलोड हो जाए डायरेक्टली। चलो ठीक है, इट्स कमिंग ऑन यूट्यूब, वो उस पर भी अपलोड करो so that we have this. Starting with the first question. Abdullah, can you see the screen? ठीक है, सब कुछ क्लियर है? Zaheb, can you see the screen? Can you hear me?
Yes, sir.
अच्छा, अब ये कि this particular paper, ठीक है, this one is probably the latest one, the one that's available at the moment. So we're going to try and do this one. और इसमें ये कि starting with the first question, ठीक है? So I haven't even done this paper as well. ठीक है, this is 2021. So the table shows the number of protons, neutrons, electrons in four different particles W, X, Y, and Z. Which pair represents the atoms of two isotopes of the same element? So that's pretty easy. Okay, isotopes. Which two are isotopes? Can anyone quickly answer this?
X and Y.
Which one?
X and Y.
ठीक है, X and Y are isotopes. They are definitely isotopes, but remember this is a trick question. He's talking about atoms, okay? The problem with this one is that if you go with X and Y, the problem is that X is not an atom, okay? That's what was, it's not an atom, okay? That because it's an ion, it's a -2 ion because it's got more electrons than protons. Zaib, is this clear?
Yes, sir.
ठीक है, एक सेकंड देना, मैं इसको बड़ा कर लूं. One second. चलिए, that's. अच्छा, so remember, okay, questions that appear to be easy, they're not always that easy, ठीक है? So X and Y, remember atoms are W. ठीक है, one of the atoms is W. And W and Y would be isotopes. They've got the same number of protons, the same number of electrons, so they definitely are not ions. They have exactly the same protons, electrons. The only difference is they've got different neutrons. So that is going to be the correct option, W and Y, that's A. Is this clear? So yeah. The next question is, where in the periodic table is the element that has an outer electronic shell arrangement of 4s2 P3? We did do this. I told you that group 1 is S1. If you talk about group 2, that's S2. Group 3 would be S2 and P1. 4 would be S2 and P2. And the next one is group 5, which is going to be S2 and P3. So it's going to be group 5, which is now called group 15. Okay, so that's group 5. Which period would it be? It clearly says that it's in shell number 4, right? Shell number 4 means that it's going to be in the 4th period. So the answer would be D. Is this clear?
Yes, sir.
That's next question. Next question is substance Q is a hydrocarbon. So when 1 gram of Q is completely burned, 3.22 grams of carbon dioxide is produced. So what could be the identity of Q? It's a combustion analysis question. It's a hydrocarbon, we know that. Okay? So that means there's going to be carbon and hydrogen atoms only. Now you're burning this hydrocarbon. We don't know how many carbons and we don't know how many oxygens it's got. Sorry, how many hydrogens it has, right? So we're not sure about that. But it says that it produces carbon dioxide, right? And any hydrocarbon, it produces two things. It produces carbon dioxide and a water molecule. So if there are X carbons, the amount of carbon dioxide would be produced would be X as well. If you've got 4 carbons, there would be 4 carbon dioxide molecules produced. So we've got 1 gram of Q. Okay, that's what is given, and we have no idea. We don't know the moles of that. So we know 1 gram of Q. And he says that it produces 3.22 grams of carbon dioxide. Can anyone quickly tell me the moles of carbon dioxide? That would be mass divided by the amount of carbon dioxide, which is 44. What do you get?
0.073.
So you're going to get 0.0773.
73.
Are you sure?
Yes.
ठीक है, no, मतलब
Yes,
it's in
sir.
this. So you're getting 0.073 moles of this, right? Uh, how many moles of this hydrocarbon you've got? Now you're not sure how many moles you have, right? So because you don't know what the MR is. Now that's why it's a trial and error question, because you're not sure what the MR is. So how would you figure out the mole, and how would you figure out the ratio? That what is the ratio? So for this, you have to do trial and error. You have to first go with the first one. Think of it, what cyclohexene. Does anyone know what the formula of cyclohexene would be? I mean, cyclohexene would be,
C6H12.
it's not going to be 12. That's again, it's a cyclic structure. That means all the carbon atoms are in a cyclic arrangement, and there's going to be at least one double bond, right? So if you start adding this H, there would be two H's with this, two hydrogens with this, there would be two hydrogens with this, and there's going to be one hydrogen with this, right? So can you quickly, can you quickly count the number of hydrogens? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's C6 and H would be 10. Is this clear?
Yes.
Yes.
ठीक है, remember in cyclic structure, it would have been C6H12 because it's an alkene. But in cyclic structures, because the ends are bonded to each other, so there are two hydrogen atoms missing at the ends as well, because there is no end. ठीक है? Otherwise, if it were a straight chain, then there would be hydrogen atoms at the end. So there would be two hydrogen atoms less. Can anyone tell me what the MR is? What is the MR? That's 6 carbons is what? 612, that's 72, I think. It's going to be 82, I guess.
82.
So how many moles, if we're talking about the first one, how many moles would this have? 1 gram to,
0.01.
so it's going to be 0.0.
12.
I said 1, 2. Be very careful about this. It's going to be 0.012 moles. And are you sure that this is exactly 3.22 divided by 44? Is this the exact value? Let me just have my own. Just a second. 3.22 divided by, so where did the 0.22 divided by 44, right? It is 0.0732. 0.073. Okay, that's fine. 0.073. I said, now, what could be the identity of P? Now, this is an issue. It would have been a lot better if carbon dioxide was a whole number, which it's not. I said, anyways, you've got 6 carbons, right, in this molecule. So that means carbon is 6, right? So how many carbon dioxide would be produced? That would be 6 carbon dioxide as well. So the ratio would be that one molecule, like one of this, like one molecule would produce how many carbon dioxides? It's going to produce 6 carbon dioxide. Is this point clear?
Yes.
So that means, and this is exactly 0.012 moles or not? 0.012 divided by the MR of this, which was, I think, 82. So 1 divided by 82. That is 0.01219. So the ratio is whatever moles you have over here, the moles of carbon dioxide that would be produced would be 6. It would be 1:6. So the moles of carbon dioxide would be 6 times more. So I'm going to multiply this by 6. What do I get? I get exactly 0.0731, the same number. So it is 1:6. Is this point clear?
Yes, sir.
So So the moles exactly fit with the description of the equation that one molecule would produce 6 carbon dioxide. We had 0.073 moles of this. We got 0.012, multiplied this by 6. We get the same ratio. It's 1:6. So the first one kind of looks all right. There's nothing wrong with this. Is this clear? Because the data is exactly fitting with the information. That
Yes.
the moles of carbon dioxide and the moles of this particular molecule, the ratio is exactly matching what it's supposed to be. So I think we should not try the other options now. I'm just going to quickly even open the marking scheme just because. One second. Because this one I haven't solved, so we can quickly check the answers as well. Hopefully the first one is the correct one. Which option was this? This is March 2021. This is March 2021, 1, 2. And this is question number 3, which is A. Okay, that's fine. It's A. So we should not try any of the other options. Next question. We've got again a moles question. It says that originally chemists thought indium oxide had the formula of INO. By experiment that they showed that 4.8 grams of indium combined with 1.1 gram of oxygen to produce 5.8 grams of indium oxide. The AR of oxygen was known to be 16. Which value for the AR of indium is calculated using these data? So the question is, there's indium, which I think is IN. It's reacting with oxygen. It's combined with 1 gram of oxygen to produce 5. Now, oxygen, when it just says oxygen, it's probably the diatomic oxygen, which is O2. And it forms indium oxide. We don't know what the formula of this indium oxide is. So that is kind of, we're not sure what the formula is. What they've given us is that there is 4.8 grams of indium. So the moles can be found out. You got 4.8 grams of indium. You're going to divide that by, or better still, actually, forget all of this. Forget the equation. I mean, let's do it the empirical formula way. Basically, what we need is we need to figure out what the empirical formula is. And they've shown us that they said that chemists thought that indium oxide had the formula INO. By experiment, they showed this 4.8 grams. So indium is 4.8 grams. If you know how to figure out, and the oxygen that is added, that is 1 gram, right? So these two combine to form 5.8 grams. So this entire thing is now 5.8 grams. Now, how do you figure out the empirical formula? They've already done that. They figured out the empirical formula. The empirical formula is, it requires 2 steps. You first find the moles, you divide by the AR. So the AR is given at 16. The AR of indium is not known, right? Is this clear?
Yes.
Yes.
And the ratio should come out to be equal to 1:1. So that means the ratio should be exactly the same. Like if you try to find empirical formula, the empirical formula, you calculate the moles divided by the AR of this, mass divided by AR of this. You find the moles and then you find the simplest ratio, right? The ratio is already provided. That means whatever number of particles of indium you've got, the same number of particles of oxygen are going to be present. So the ratio is going to be exactly the same. So if the ratio is the same, you just have to make them equal. So that means 4.8 would be, you bring the 1 over here into 16, and that's basically equal to your AR. What answer do we get?
76.8.
Okay, which is why it's going to be 77 then. So the answer to 4 would be option B, and it's option B. So just make sure that it's the same empirical formula question. Instead, the empirical formula is already provided. You already know the ratio. You know it's 1:1, so that means whatever you're going to get over here, the same moles would be over here as well. So you're just going to equate the two together. Is this clear? So
Yes.
next one. So now the next one is, in which substances are the only intermolecular forces temporary dipole, induced dipole attraction? These are van der Waals forces. Now, remember van der Waals forces, temporary dipole induced dipole forces are always present in molecules. What is the background of van der Waals forces? Van der Waals forces are that if you have a molecule, let's say we take an H2 molecule, the electrons, they don't have an electronegativity difference, so the electrons are evenly distributed between the two atoms. But during collisions, like you have lots of H2 molecules, what happens is that although it's a neutral molecule and the electrons are evenly distributed, but what happens is that during collisions, the electrons might get knocked to either side. So temporary dipoles can be produced. This side could become partial negative, this side could become partial positive. The electrons might, for a very temporary instance, might shift to the right or might shift to the left, resulting in temporary dipoles, and that would result in induced dipole. The electrons over here would, because of the negative charge over here, the electrons over here would be repelled as well. So this side would become negative, this side would become positive, and the two molecules would start to attract each other. Is this clear?
Yes, sir.
So the point is, every molecule has that. The electrons are always fluctuating. They are always shifting around. Okay? Because they're always, all the molecules are bumping around, right? Now he's saying it should have only these forces. Now, apart from van der Waals forces, which are always present in molecules, there are other types of forces that can be present as well. So starting with the first one. So remember, van der Waals forces, these fluctuating dipoles, temporary dipoles, induced dipoles, they're always present. Let's talk about HCl. Can anyone tell me quickly, apart from van der Waals forces, what other intermolecular force is present in an HCl molecule?
Permanent dipole attraction.
Okay, so there's going to be a permanent dipole because chlorine is electronegative. So chlorine is going to attract the electrons slightly more strongly. This side would become positive. This side is partial negative. This side would be partial positive. So there's going to be a permanent dipole. The negative Cl would be attracting the positive H, and that is a permanent thing. It's always going to happen. Okay, so it's not like the electrons are randomly fluctuating around. The electrons would always be close to Cl. So that's a permanent dipole. Apart from van der Waals forces, this will have permanent dipoles. What about a methanol molecule? A methanol molecule has an OH. When something has an OH, what type of attractive force do they have?
Hydrogen bonding.
Okay, they're going to have hydrogen bonding. That's like a permanent dipole, but a much stronger version of it because oxygen has these lone pairs. Because of these lone pairs, high electron density lone pairs, the negative charge on this oxygen, partial negative charge, is really, really strong. The H would be partial positive. So this would be partial negative, this H would be partial positive. So the positive H would be attracted to the lone pairs on oxygen. So it's going to be a very strong attractive force that's known as a permanent, not a permanent dipole, that's known as a hydrogen bond. So it will have van der Waals forces. The molecules will be knocking around, getting knocked around, and there would be electrons fluctuating around. But the main attractive force in this would be hydrogen bonding. I said now C is octane. Octane is just a bunch of carbon atoms. It's just lots and lots of carbon atoms. 8 actually. Octane is C8 and H is 18. Now, octane will have only van der Waals forces. Why? Because carbon and hydrogen atoms have almost the same electronegativity. So, which means that a carbon-hydrogen bond, like if I do a simpler molecule, octane is a much bigger molecule. The carbon and hydrogen atoms, they don't have any electronegativity difference. What that means is that the electrons are all evenly distributed around. So the electrons are, I mean, this side is not partial positive, this side is not partial negative. So the only thing that's happening is that this molecule is bumping around. So the electrons kind of get randomly, sometimes they get pushed to this side, sometimes they get pushed to this side during collision. So a hydrocarbon always has only van der Waals forces. It only has electrons getting pushed around due to random collisions. And what's the attractive force in water? उसमें क्या है?
Hydrogen bonding.
ठीक है, water has OH bonds as well, so that's hydrogen bonding as well. So that is hydrogen bonding. So moving on to the next one. Is this clear? Previous question.
Yes, sir.
Clear? So you've got the next question is a solution contains 0.25 grams of sulfur in 1 dm cube of water, and which volume of sulfur dioxide measured at 50 centigrade and pressure 1 times 10 power 5 must be added to 1 dm cube of water to produce the solution. So the thing is, firstly, he's talking about the sulfur dioxide gas, and he's saying must be added to 1 dm cube of water to produce this particular solution. So this is about sulfur dioxide, and this is about PV is equal to nRT because remember sulfur dioxide is a gas. So what volume of sulfur dioxide must be added to 1 dm cube of water to produce this solution? So sulfur dioxide is a gas, which is a very soluble gas. So you're adding this gas to water. Now the pressure is given. The pressure is 1 times 10 power 5. So that is with you. The volume is not known. That is what we are looking for. What volume? So volume is not known. Remember, in PV is equal to nRT, you have to be careful that pressure always has to be taken in pascals. The volume that you're going to get is you're going to get the volume in meter cube. N is moles. So you can find the moles because he's talking about 1 dm cube of water. 1 dm cube of water, it contains 0.25 grams of sulfur dioxide. So you can convert that into moles. Mass divided by the MR, sulfur dioxide would probably be 64, I think. It's sulfur is 32, oxygen is 16 plus 16, so that's so you get the moles. R is a gas constant, that's 8.31, and T is temperature. Temperature must be in Kelvin. So 50 degrees centigrade is basically you add 273 to it. So that's going to be, I think, 323 Kelvins. So try and figure out what the volume V is. And always remember the units. In PV0 nRT, this is pressure in pascals, this is meter cube. That's the moles, that's the gas constant R, and the temperature should be in Kelvins. Can anyone quickly try and tell me what the volume is? For this. Zaib, are you calculating this?
0.1048.
0 point?
1048.
1048, that's approximately 105, but that's in meter cube, right?
No, centimeter cube.
I say you converted it into centimeter cube, so it's going to be B. Because this one is going to be B. And we can quickly, now in this question you have to be very careful about the units because whether you get 0.105, whether you get 105, I mean the error would be in the units. So be very careful when you're trying to convert units. Meter cube to cm cube, that's multiplied twice by 1000. So the answer to this one is for 6, it's going to be D. For 6, it's 105. Zaib, can you spot the error?
Oh, I
Did you
I
convert
assumed that
this?
the volume was DMs.
Achha, you assumed
I
the volume was.
converted into decimeter cube.
Achha, theek hai. Nee, what was the volume that you were getting in meter cube? Tell me that. Achha, anyways, you're going to multiply this by 1000 again, and you'll get D. Theek hai, that was, I mean, remember I told you this was going to be the error. What is the volume that you got originally in meter cube?
In meter cube, it was 1.05 into times 10 power minus 4.
10 is per minus 4, right? So you're going to multiply, if you want to convert meter cube to cm cube, you multiply it twice by 1000. So that's going to be multiplied by 10 power 6. And this would become 1.05 times 10 power 2, which is basically 105. That's the next one. An experiment was performed to determine the enthalpy change of combustion of ethanol, and this is probably a Q is equal to MC delta T question, right? So the data collected are shown. He's trying to, what is he doing? He's trying to determine the enthalpy change of combustion of the ethanol, right? So you're burning and you're heating the water up. So what energy is being absorbed by the water? That's the question. So the mass of water, what's the mass of water given over here? The mass of water given is W grams. So we have W, right? So we've got W. I'm just going to write W, not grams. So it's going to be W. What is the specific heat capacity of water? That's it's given over here. That's 4.2. So it's going to be multiplied by 4.2. What else? Delta T. What's the temperature change? Have they given us the temperature change? The temperature rises y degrees centigrade. So that means it's going to be into y. That's it. And it's exothermic. That's why you're going to have a minus sign over here. Remember, in calculating delta T, you don't actually have to convert it into Kelvins because the change is always going to be the same. Whether the change is 2 degree, is it in Kelvins or centigrade, it's the same change. So you don't have to convert the values, it's just going to be y. So that's your Q. Now the mass of ethanol burned is also given. And the MR of ethanol is also given. So this enthalpy change is for how many moles? This is for X grams divided by the MR, which is Z. So these many moles, they produce this much energy, W into Y into 4.2. Is this clear?
Yes, sir.
Yes.
So I found the moles. The mass of ethanol that's burned, mass divided by the MR of ethanol, which is Z. So that's the moles mass divided by MR. And so I found the moles and I did MC delta T and I figured out, I put the minus sign over there. Why? Because actually all the options had minus signs, so you probably will not be getting that wrong. But it's temperature rise, so it's exothermic, right? So now enthalpy of combustion. Enthalpy change of combustion is for 1 mole, so you're going to use ratios. So what energy would be produced if 1 mole of this burns? So you crisscross and you have to find X, like how much energy would be produced. Like these many moles, they produce this much energy. 1 mole would produce how much? So it's going to be, X would be what? If you divide the two things, it's going to be minus W times Y times 4.2, and the whole thing would be divided by X over Z. So in a way, it's going to be multiplied by Z over X. So that's going to be our answer. It's going to be WYZ minus 4.2. I think this one, not 1000x. Where did 1000? Why is 1000 coming in? Can you even spot the error? Where did we? How did 1000 come over here? Just a second, quickly. Repeating everything. MC delta T.
Sir, I think it is because it's in grams, right? So grams to kilograms, maybe.
No, you don't need to convert because the C is also in grams. TK in chemistry you deal in grams,
Acha,
right?
sahi. Okay.
So MC delta T, be very careful. W, that's the mass of water that's being heated. 4.2 is the specific heat capacity of water, and Y is the temperature change. TK, that's MC delta T. So these three things, right? And then you have so it's coming in from here because the heat energy that we are measuring, that's going to come out in joules, right? And he's asking that in kilojoules. So whatever value that we are getting, that's coming in joules because the specific heat capacity was in joules. So all our answers were in joules. So you have to convert that into kilojoules. How do you convert that in kilojoules? You divide by 1000. Is that clear?
Yes.
So this is where the 1000 is coming in from. So it's going to be, I think it's going to be A. I mean, that's the expression that we are getting. It's 4.2 WYZ divided by 1000x. So that's our That's where the 1000 is coming in from. I said next one is, as anyways, this one is the March paper is kind of a tough one because it requires a lot of calculations, so it's pretty time consuming. You have this question: which row about this reaction is correct? So the equation is given. He's saying vanadium is oxidized. So let's look at vanadium. What's happening to it? He's already told us that Cl is -1, right? So what's happening to vanadium? Vanadium is over here, and you've got vanadium over here as well, and you've got vanadium over here as well. So is it getting oxidized? Is it getting reduced? First thing, try and find the oxidation state of vanadium. Vanadium is unknown. There are 2 oxidants, so that's -2 times 2. And there's 1 Cl, and he's already told us that Cl is -1. He's already specifically told us that Cl is -1. So all the charges, they must add up to be equal to 0, because this molecule over here is completely neutral. So all of these things, they should add up to be equal to 0. So what is V coming out to be? I mean, what's the value of X? That's going to be -4, -1, that's -5. So X would come out to be equal to +5. Is this clear?
Yes, sir.
So what about VOCl2? Again, he's saying that its Cl is -1. So VOCl2 is X, oxygen is -2, there are 2 Cl, so that's -1 into 2. So that's, I think, -4. This entire thing should be equal to 0. So I think over here X is coming out to be +4, right? So is this clear?
Yes.
So you've got VOSO4 as well. So SO4 is -2. I mean, this part over here is -2. So that means VO is actually +2. I mean, that's if you know that if you have FeSO4, SO4 is -2, Fe is +2. So VO over here is +2. So we can try and figure out that VO is +2. So what's the oxidation state? That's oxygen. Vanadium is Vx. Oxygen is -2. They should all add up to be equal to +2. So I think X would come out to be -2 goes on the other side. That would come out to be +4. So I think vanadium is +4 on both sides. So vanadium goes from +5, like originally it's +5 over here, and now it's +4 over here and +4 on over here as well. That means it's getting reduced, right? Is this clear?
Yes.
Yes, sir.
And iodine is getting oxidized. That's obvious because iodine is -1. Over here it's 0. So that means the oxidation state of iodine, it's increasing. When it increases, that means oxidation is taking place. As a question number 9, in which reaction is water behaving as a Bronsted-Lowry base? Base, what's a base? Base accepts H positive ions. So where is water behaving as a base? That's B. You got water, now it's H3O plus 1. So what did it do? It accepted an H plus 1. Is this clear?
Yes, sir.
Yes.
So this one was simple. It simply accepted an H plus 1. That's it. So it's a base. A large excess of marble chips is reacted with HCl. How is this result different when the reaction is repeated with 60 cm3 or 0.5 mole per dm cube hydrochloric acid at 40 degrees centigrade? First thing, the reaction temperature is the same. So temperature is not a factor. This is a kinetics question. So the temperature is not a factor. Okay, so temperature is out. Temperature has no effect. This one is more concentrated. This one is less concentrated. So this one would be a faster reaction, right? And this one would be a slower reaction. Is this clear as well?
Yes, sir.
Yes.
So the reaction is going to be slower. So it's going to be either option C or option D. I mean, the second reaction is the one that's going to be slower. It would take a longer time. But would you get more products or would you get less products? How many moles do you have in total of HCl? Volume into concentration. What do you get? I mean, what's 25 into 1 divided by 1000 volume into constant.
0.025.
So you got 0.025 moles, right? What about the second one? How many moles you got over here?
0.03.
0.03.
So the second reaction, although it's slower, okay, that's a given, it's slower, but it's going to produce more products because you have more moles of it. So it's going to be more of the products are made when the reaction is complete. So it's going to be C. It's going to be a slower reaction, but it's going to give you more products. Okay, is this clear?
Yes.
So next one, let's move to question number 11, which is a Bronsted-Lowry acid. Not a Bronsted-Lowry question. It's a Boltzmann distribution. Now, in a Boltzmann distribution, you have distribution of energies of particles in a container or a solution. At high energy, the number of particles are very less. At low energy, the number of particles are very less as well. I mean, the height is the number of particles. Most of the particles have energy that's like at the average energy, the number of particles are a lot. I mean, the height is the number of particles. So, for example, if you're sitting in your room at 25 degrees centigrade, that's the most particles would have energy that would be corresponding to 25 degrees centigrade. Very few particles in the room would have energies that would be really high or really, really low. Now, he's saying, how does the diagram appear if the same reaction mixture is at a higher temperature? What happens at a higher temperature? At a higher temperature, the number of energetic particles increases. So the curve rises from the side, and the number of like particles having less energy, that decreases. So the curve kind of drops on the side. Is this clear?
Yes, sir.
Okay, so if you increase the temperature, you get more particles at higher energy and you get less particles at lower energy. So the curve kind of flattens out and it rises from the right side. Okay, that's a pretty bad curve. Just a second. So it rises from the right side and drops from the left side. And the overall, because the particles are now distributed over a wider range of energy, so the overall at any particular energy that you don't have a lot of particles, so the curve kind of starts flattening out. So the curve is unchanged. That's obviously wrong. So the values of both EA catalyzed and EA decrease. Remember, you're just changing the temperature. The activation energies, nothing happens to them. The only thing that changes activation energy is a catalyst. I mean, it's temperature is not going to. The only effect the temperature has is that now this is the cutoff point. Like particles having energy that is lower than the activation energy, they're not going to react successfully. And particles that have energy that are greater than the activation energy, they're the ones that are energetic and they're able to react successfully. So the activation energy point remains exactly the same. So the values of both EA catalyzed and EA, they remain the same. Okay? Only one thing changes EA, and that's a catalyst. That's the presence of a catalyst. Okay? Is this clear? Okay, is this clear?
Yes, sir.
I said next one. Which observations are made when a sample of silicon chloride is added to a beaker of water? So this is part of inorganic, which you just have to memorize. Okay, I'm going to send you notes for this as well. This is the reaction of chlorides with water, right? You have to remember period 3, and you have to remember each one of them. Like what happens when you react a chloride like NaCl with water with MgCl2 with water. So this is what happens. I'm going to do just a quick revision of period 3 somewhere over here. Just a second. Okay, so I'm going to open up the inorganic notes, which I think it's this one. SiCl4 with water would hydrolyze. So this is your period 3. So these are your reactions of chlorides with water. What happens is, I'm just going to mark on this. What happens is that NaCl, the first one, NaCl, it simply dissolves in water. Nothing happens. It just dissociates, ionizes. There is no hydrolysis. With MgCl2, again, it simply mixes with water, but there's very little hydrolysis, very slight hydrolysis. So some HCl might be produced, which is why the pH is not exactly neutral. It's 6.5 because an acid is getting produced. When it comes to AlCl3, the hydrolysis becomes really strong. There's a very vigorous reaction with water, and fumes of HCl are produced and aluminum hydroxide. So the pH really drops because a lot of HCl is produced. And the hydrolysis becomes more and more powerful. SiCl4 again hydrolyzes. So they're going to result in a very strongly acidic solution. Fumes of HCl would be produced and a white precipitate would be seen. So remember, you should revise all your inorganic. That's mostly memorization, nothing to it. So steamy fumes and a precipitate are both observed. HCl gas with SiCl for HCl gas is produced, and a precipitate is going to be produced with silicon. Silicon and AlCl3 would kind of have the same reaction. SiOH4 is produced, and HCl is also produced along with it. Is this clear?
Yes, sir.
Yes, sir.
So which row is correct? The first ionization energy of phosphorus is greater than that of magnesium. So it's about ionization energy. So across the period, what happens when you move across the period? Now, phosphorus and magnesium are kind of in the same period. So ionization, I'm just going to Google this ionization energy and look at a graph. So this is your graph. There are dips at group 3 and 6. But otherwise, across the period, ionization energies kind of look like this. They keep on increasing when you move across the period. They kind of keep on increasing. So he's talking about phosphorus, which is over here, and he's talking about magnesium, which is over here. So the ionization energies, they keep on increasing across the period. It becomes very difficult to actually remove electrons when you move to the right. So what's the reason? Why does it become more difficult when you try to remove electrons? And the reason for that is that when you move across the period, you have the atom size, you have more protons, there are more and more protons. So there's more nuclear attraction. It becomes much harder to remove electrons. Phosphorus has 15 protons, right? Whereas Mg has a total of 12 protons. So 15 protons would have a much stronger attraction for electrons. So that's one of the key reasons. Another reason is that the shielding and the distance are kind of the same. I mean, all atoms, they have the same number of shells, and the distance slightly gradually decreases because when you move to the right, because of greater attraction, the shells are more strongly attracted. So the distance also slightly decreases. But the number one factor is you got more protons. So it kind of becomes harder to remove electrons. So I think in this question, they were specifically talking about this. Why is it greater? Because you have more protons. So the reason is wrong. So that's why the first one is, I mean, this part is true, but the second reason is wrong. I said, what about the next one? And let me just sort of, I said the next one is the melting point of phosphorus is greater than that of magnesium. Phosphorus has more valence electrons than magnesium, which is true, but that doesn't really affect the melting point. And the melting point is also not greater. Remember, magnesium is a metal. Phosphorus, on the other hand, is a molecule, a covalent molecule. Molecules always have lower melting point. So this one is also wrong. And this is also part of inorganic in period 3. If I just open period 3 again, about melting points. Just a second, let me close this. It's about melting points. Here's a sketch of the melting points, like magnesium. I mean, this one is slightly lower. So anyways, I can't write. Phosphorus is simple molecular. It's a simple molecule. It's got van der Waals forces, so it has a low melting point. So that's why the answer to that question is I mean, this first statement is wrong altogether. Then the atomic radius of phosphorus is smaller than that of magnesium, has greater. I mean, this one is correct. We just talked about this. Like magnesium is 12 and phosphorus is on the right, that's 15. So phosphorus has more protons, which is why it will attract its electrons more strongly, which is why it's going to be smaller. So the atomic radius of phosphorus is smaller. Why? Because it's got greater nuclear charge, it's got more protons. So option C is the correct option. Okay. Is this clear?
Yes.
Yes.
चलो ठीक है, we're done till 13. ठीक है, so let's hopefully continue tomorrow then. ठीक है, with the same paper. We're going to try and solve this paper in hopefully 3 days. If you need any notes, etc., do ask me. ठीक है?
Sure.
Alright, sir.
चले,
Thank you.
okay, take care. Allah Hafiz.
Allah Hafiz, sir.
Allah Hafiz.